Hi guys, I'm going to create this video to show you how to machine custom threads using Inventor HSM or HSMWorks. It's actually possible to do this in HSM Express for Inventor, but also HSM Express for SolidWorks. So that meaning you can do that with a free product. I actually got stumped by this last week. My background is for the last decade has been woodworking, so I've kind of lost touch with threads and in the engineering side of things. But a customer on site while I was doing a demo asked if HSM was capable of machining a custom thread using a single tipped 3-pointed disposable blade and a boring bar. He wanted to machine a thread right to the bottom of a hole, and he couldn't use a taper. He couldn't use a tapping tool because they extend too far beneath the hole. So, in some cases, it was impossible to program at least those types of threads on his CNC machine. It threw me initially because I could see that there were the commands I needed, but there wasn't a tool definition. There wasn't a tool defined, or there isn't a tool type that you can use to perform this type of operation. So, having spoke to my colleague Gavin Bath, I felt like an idiot. Afterwards I had a feeling that I needed to create a form tool, but as it turns out, it was as simple as that. So in both SolidWorks and Inventor, it doesn't matter. You define the tool in the same way. Start with a sketch. Now in Inventor, I've actually created a parametric version of this tool so that in the future I can come in and adjust all these values here, which translate directly to the specifications of the ISCAR tooling. In this case, I've used the IRMJ boring bar as the foundation for the tooltip, essentially, the cutting tip, essentially. So I can reuse this tool over and over again for all the different types in the future. From there, I've defined a custom tool. So in the tool library, I've selected to create a new mill tool. I've changed the type to form mill, and I've imported the file, and then adjusted the values to suit. Now, interestingly, Inventor adds the full accuracy of this dimension here, but in SolidWorks, it rounds it directly to 2 decimal places. Anyway, so I tweaked the rest of these values as needed. As you can see here, that doesn't represent the tool that I've modelled. So if I flip that, now it does. And the cutting point isn't actually on the tip of the thread cutting face here. So I know that in this case that's 0.8 of a mil away, and so now that's in line. So as a result, the tool is now going to cut. The tool path is going to be generated in the correct place relative to the tool. Again, there's another video I created a few weeks back explaining how to do this, so I won't cover it in too much detail. But you can set all of this lot up and define the holder that you need as well. So here's one I prepared earlier. In the Inventor model, I've actually modelled the thread just because I wanted to try and see compare the model to the stock definition. As it turned out, it didn't work out all that well because there's no control over the start point of the thread when you define the operation inside Inventor HSM. Now, the reality is that that's not an issue in the real world, but anyway, all the same, I chose to use the bore strategy here. I used a 10mm tool, 10mm flat tool. You should use a boring tool, but I haven't in this case. I've selected the conical face in here, and in actual fact, I'll just take a couple of steps back there because I've modelled this thread. I've actually, before I modelled it, I offset the surface by 0mm so that I could use that surface to define my toolpath later on. So going back into the boring strategy here, I've kept the height offsets exactly to the top of the stock and the bottom of the stock, or in the whole top, the whole bottom, and I've added 4 step overs this step over is calculated as half of the tool diameter. And yeah, so that's it. I've set a pitch of 1 mil in this case, and that's it. I've got this pretty cool looking tapered boring cycle that's in here, so that works well. I've just left the links and lead-ins and outs, transitions, etc. just as default, And then with the thread, I've selected the tool in the first tab, and then the conical face for the second option. I've put the top height and the bottom height, so I actually want to make sure that the thread cuts right at the top of the hole. So here I can add 2 mils. So now you can see the toolpath popping at the top. So I know for sure that it's cutting, and I want it to go below 2 mils as well. So now it completely cuts the thread right through the job to get a nice start and end to the thread. So I've used a pitch diameter offset of 0.7 mils here. So and just so it's easy to see, I've set the compensation type to in control instead of in computer. That way I can see the toolpath is actually sitting inside the stock here. So I know that when I enter this value, the pitch diameter offset, that it's actually going in the right direction. Okay, you can, once you've got that set up, you can always switch it back to in computer or whichever, or where, which adds the G41, G42 codes in the outputted code in the during post processing. So I'm just going to set it to in computer here. Direction is climb, and I can set whether it's right-handed or left-handed, which means the tool will either start at the bottom of the hole and work the way up, or at the top and work your way down. And so that is it. Now, it is exactly the same in SolidWorks, and just to show you, I haven't modelled the thread here, but the boring cycle is the same. It's very similar selections here as well, and yeah, the things are in a slightly different order, but the same logic applies. Again, here at this stage, remember to add some stock to leave, because obviously you want to make sure that your thread milling is doing all of the finish machining, and linking is pretty standard as well. And just to show you, the threading is much the same. So tool selection, feeds and speeds, face selection. In this case, I've just selected the solid face because I didn't model the threads, and I've got my offsets in the same way here for the working planes. Now, I didn't cover this in the Inventor side of things, but here I've selected to cut this in multiple passes. I wanted 2 step overs at 0.2 mils, and I've also added repeat passes down here, which means, so essentially we're going to end up cutting this toolpath's going to run 3 times, twice to remove the stock, and then there'll essentially be 2 finishing passes just to make sure the thread is perfectly clean. And because I can in SolidWorks, I'm going to do a stock simulation and simulate the whole lot, and so you can see the final result. There'll be a little bit of a delay here because it does take a while to do, especially the thread machining. So yeah, there we have it. I've not done the best job here with my toolpath. I've got a little bit of a disc left in the bottom, but that's something that can easily be cleaned up. But the important part is that we got to see that as a result of using the stock simulation here. So you can see that the thread's been cut nicely. So yeah, again, to repeat, that is this strategy is available in HSM Express. So it's in the 2D, the 2.5 axis side of things. So although a thread is actually continuously moving in the Z-axis, it's technically a full 3D operation, but Autodesk have included the ability to do that in the free 2.5 axis product. Yeah, so well done Autodesk, and I'm pleased to have learnt something new. Next time somebody asks me that on site, I'll be able to do it on the spot. So a little bit embarrassing, but pleased to have learnt something new. Alright, have a good day people, and thanks for watching, and we'll see you next time.